Hi everyone, I am Vasanti, Assistant Professor Department of Mathematics, working on Bharathiyar Arts and Science College for Women, Devekuruchi. In this video, we are going to discuss about the topic group theory and its applications. Okay, first of all, who is father of group theory? Early 9th century, the earliest study of groups as such properly goes back to the work of Lagrange in the late 8th century. However, this work was somewhat is isolated and 1846 publications of Augustin Louis Cauchy and Hallis are more commonly referred to as the beginning of group theory. Okay, next I will discuss to learn history of group theory. The history of group theory, a mathematical domain studying groups in their various forms, has evolved in various parallel thoughts. There are three historical roots of group theory: the theory of algebraic equations, number theory, and geometry. Okay. Next, introduction to group theory. Group theory is the branch of pure mathematics which is emanated from abstract algebra. Due to its abstract nature, it was seeming to be an art subject rather than a science subject. Group theory in modern algebra, the study of groups which are system consisting of a set of elements and a binary operation that can be applied to two elements of the set which together satisfy certain axioms, that is closure, associative, identity and inverse. Okay, next I will discuss branches of group theory. It is four types. First one finite group theory, second one representation group theory, third one Lie theory, finally fourth one geometric group theory. It is very important of the branches of group theory. Okay, first one finite group theory. Finite group is a mathematical group. The finite number of elements is finite group. Consider any finite set which is supported any operations to each pair of elements is a finite group. Second one, representation theory. Representation theory is also mathematical branch which is also studied abstract algebraic structures by representing vector space and models. It is also useful method because it reduces problem in linear algebra and the subjects well understood. Okay. Third one, Lie theory. In mathematics, researchers observe lie insulated lines of study involving integrations of differential equations, transformation groups, and a contact of spheres that have come to be called Lie theory. The subject is part of differential geometry. Okay, finally, fourth one, geometric group theory. Geometric group theory is that it is the study of groups as geometric objects. Thinking about groups this way was popularized by Gromov, who revolved the subject of infinite groups. The simplest way of regarding a group as the geometric object is through its Halley graph. Okay, next I will discuss definitions. First one, group. Let G be a finite set of elements together with a binary operation star that together satisfy the four fundamental properties of closure, associativity, identity and inverse. Okay, first one, closure property. Consider any two elements in capital G, then product of two elements also capital G, that is a comma b belongs to G implies a star b belongs to G for every a comma b belongs to G. Therefore, it is satisfied closure property. Okay. Second one, associativity. Consider any three elements in capital G, that is a comma b comma c belongs to G, which is satisfied the following conditions: a star of b star c equal to a star b star c for every a comma b comma c belongs to G. Therefore, it is satisfied associative property. Okay. Third one, extension of identity. There exists a unique element E belongs to G such that A star E equal to E star A equal to A for every A belongs to G, where E is a identity element of G. Okay. Finally, fourth one, extension of inverse. For every element A belongs to G, there exists a unique element B belongs to G such that A star B equal to B star A equal to A, where B is a inverse element of A and we write B equal to A inverse. For example, the set of integers complex numbers are group it under the operation star. Okay. Next definition, abelian group. A group is abelian group which is satisfied commutative law, that is A star B equal to B star A for every A comma B belongs to G. Okay. For example, the set of integers, the complex numbers are abelian group under the operation multiplication. Okay, next is definition, subgroup. A non-empty subset H of a group G is said to be subgroup under the operation star if H is itself a group, that is H contain or equal to G. For example, consider this set G equal to set of all 1 comma minus 1 comma I comma minus I and H equal to set of all 1 comma minus 1. H is a subset of G. Therefore, H contain or equal to G. Therefore, H is a subgroup of G. Okay. Next one result. A non-empty subset H of a group G is a subgroup of G if only if first one A comma B belongs to H implies AB belongs to H. Second one, A belongs to H implies A inverse belongs to H, where A inverse is the inverse of A belongs to G. That is, it meaning for any consider this set H is a subgroup of G, then satisfy only two conditions, that is closure and inverse. Okay, next topic, order of a group and order of an element of a group. First one, order of group. The finite number of element is called an order of group. It is denoted by order of G. For example, consider the set G equal to set of all 1 comma minus 1. Then the element are 1 comma minus 1. Therefore, the order of element is 2 with the operation multiplication. Okay. Second one, the set of all integers Z is an infinite group with respect to operation addition. This is already we know that, but Z is not a group with respect to multiplications. Okay, next definition, order of an element of a group. Let G be a group under multiplication. Let E be the identity element in G. Suppose A is any element of G, then the least positive integer n if exists such that A power n equal to E is said to be order of the element A, which is represented by order of A. In case such a positive integer n does not exist, we say that the element A is of infinite or zero order. For example, consider the multiplicative group G equal to set of all 1 comma minus 1 comma I comma minus I of fourth roots of unity have order of elements is first one 1 power 1 equal to 1, that is order of 1 equal to 1. Second one minus 1 whole square equal to 1, that is order of minus 1 equal to 2. Third one, I power 4 equal to 1, that is I square into I square equal to minus 1 into minus 1 up. Therefore, order of I equal to 4. Finally, fourth one is similarly to I. Minus I square into minus I square equal to 1 into 1. Therefore, order of minus I equal to 4 respectively. Therefore, the order of elements is 1, 2, 4, 4. Okay. Second one, consider the additive group Z equal to set of all minus 3, minus 2, minus 1, 0, 1, 2, 3 is a infinite order. Since 1 dot 0 equal to 0, therefore order of A is infinite. Next theorem, Lagrange's theorem. First statement, the order of each subgroup of a finite group is a divisor of the order of the group. That is, order of H is a divisor of order of G. Proof, let H be a subgroup of G and order of G equal to n and order of H equal to m. To prove m is a divisor of n, that is, order of H is a divisor of order of G. First, I will consider the mapping for left and right coset. It is satisfying the condition 1 to 1 and on to. Since H and H are distinct and G is a finite number of distinct right cosets of H will be finite, say P. the union of B distinct right courses of H is equal to G. Now G equal to H union, HA union, HB union up to etc. where A comma B up to etc. belongs to G. Next, taking on ordering on both sides, then we get the result order of G equal to order of H plus order of HA plus order of HB. Since order of G equal to N and order of H equal to M, then applying these conditions, then we get the result N equal to M plus up to etc. P terms. Okay. Next line, N equal to MP, then P equal to N divides M. Therefore, order of H is a divisor of order of G. Hence, order of the subgroup of a finite group is a divisor of the order of the group. Hence, the proof. Next, one note, the converse of Lagrange's theorem is not true. For example, consider the subgroup P4 of permutation degree 4. Therefore, order of P4 equal to 4 factorial equal to 24. Then order of A4 equal to 24 divided by 2 equal to 12, such that order of H equal to 6. Therefore, 6 is a divisor of 12, that is order of H is a divisor of order of G. This example check the Lagrange's statement. Next, applications of group theory. Group theory has applications in physics, chemistry, material science, and even puzzles like Rubik's Cube can be represented using group theory. Group theory is also central to public key cryptography. Okay, first one, physics. The relations of group with symmetry means that group theory plays a hung role in the formation of physics. Fundamental in modern physics is the representation theory of Lie groups. Okay, second one, chemistry. In chemistry, group theory is to describe symmetries of crystal and molecular structures. This is then important in understanding the physical and spectroscopic properties of materials. Okay, finally, thank you.